afternoon. This is Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. Today we will discuss experiment number 4, LeChâtelier's principle and buffer solutions. The objectives of this experiment: to study the effects of concentration and temperature on a chemical system, particularly in the equilibrium state. To study the effect of strong acid, strong base conditions additions to a buffer system, and to observe the common ion effect on a dynamic equilibrium shift, either shift to the left or the right, depends on your activities. Introduction. Because of the reaction characteristics, most of the chemical reactions do not produce 100% yield. After a period of time, the concentration of reactants and the concentration of products stop changing. You no longer observe net change in terms of concentrations. This stopping of the reaction before finishing implies that the system has reached a state. This state related to one important condition: the rate of your product formed and the rate of reactant being reformed are the same. So the rate for the forward reaction is the same as the rate for the reverse reaction. Then, for example, if you have this reaction, you have this dinitrogen tetraoxide, which is brown colored materials. This reactant is going to be produced 2 moles of nitrogen dioxide gas. So what you see this dinitrogen tetraoxide break down to nitrogen monoxide at a certain time. So this color is no longer changed. So you see, whenever you see the color change, so this dinitrogen tetraoxide is slightly brown. Whenever you produce nitrogen dioxide, the color becomes a little darker brown. With the time going through, the color keep changing. At a certain time, you no longer observe the color change. No net change in terms of the formation of nitrogen dioxide. So this is nitrogen dioxide. At this point, you consider this reaction reaching the equilibrium from the macroscopic and the molecular perspective. At this point, you consider the equilibrium. The equilibrium applies to the extent of a reaction. At this point, the concentration of your product, which occurs after an unlimited time, or you can say no longer change. Concentrations of your product no longer subject to the change. At this equilibrium, your forward reaction rate is the same as reverse reaction rate, as we discussed in your previous experiment, equilibrium. And the state of the system at equilibrium is considered a dynamic system. So from your molecular perspective, so what you are going to observe, no further net change will be seen, because the change in one direction are balanced by the change from the other. And then at this point, as we already know, the rate for the forward reaction is the same as the rate for the reverse reaction, meaning your K forward multiplied by the reactant concentration to the power m equals to the rate for the reverse, rate constant for the reverse, multiplied by the product concentration to the power n. You take the ratio between these two K's. For forward and reverse reaction rate constant, you are going to receive this product concentration over concentration of reactants. This division, this ratio is called the K. The capital K is called the equilibrium constant. This smaller k is your rate constant. This equation is also known the law of mass the law of mass action. The value n and m, they are the coefficients of your reactant and the product at your balanced reaction. So at this point, you consider the equilibrium. Equilibrium is the degree, is the extent, is not kinetics. The rate for your forward reaction and the rate for the reverse reaction, again, are equal. Doesn't mean the concentration of reactant and the products are the same. So be advised. Concentrations of reactant and concentrations of product are not necessary to be the same. So when you apply external stress into this equilibrium, what's going to happen? Equilibrium is going to subject to the shift. So at this point, we are going to consider the condition is called a dynamic equilibrium. And this dynamic equilibrium is a characteristic of all reversible reactions. For example, your nitrogen dioxide produces dinitrogen tetroxide. So you are going to release 58 kilojoules of the heat. So if an external stress is applied to this system at its equilibrium, the equilibrium is shaped in the direction in order to minimize the effect of the stress. What does this mean? When a system at equilibrium is subject to the stress, the system returns to the equilibrium by shifting to reduce the stress. For examples, you are going to have several factors affecting on the equilibrium position. Number one, the changes in concentration. Number two, the changes in temperature. Number three, the changes in pressure. If the concentration increases, your system is going to consume more of that increase. If the concentration of reactant increases, your reaction will shift it to the forward direction. Otherwise, product concentration increase, reaction will shift it to the reverse direction. So that's what you are going to observe. So here is the example. You have your concentration, initial concentration, you have a disturbance, you have the new initial, and you have the change, you have new equilibrium. So the equilibrium constant K will be a constant value. Initially, what you did, you adding 0.2 this PCl3 gas and 0.125 Cl2 gas together to produce this PCl5, which you have 0.06 mole per liter. And then you apply a disturbance. You apply external stress. You adding chlorine, Cl2, you adding chlorine 0.075. What's going to happen? This will make something change. Your new initial for this first reactant, there's no change, 0.2. Due to the addition of this 0.075, chlorine concentration also becomes 0.2. Your product PCl5, so still 0.6. And then you are going to determine the new equilibrium shift. So you are going to consider X for the different reactants and products. For products, you use positive sign. For reactant, you use negative sign. Negative because you consume them. Therefore, at new equilibrium, so you are going to have the 0.02 minus X, and similarly for these two. And then your final products, so will be 0.06 plus X. So the equilibrium will be stays the same. So you can determine how much of this reactant further going to be produced. This reactants will be reacted, this product will be produced. after a new equilibrium, what you found, the concentration of this final product becomes 0.637 mole per liter, meaning your reaction shifted to the right, favorable to the right, in order to decrease this addition. So that's the example. Let's take several examples. We are going to predict. So what's the effect of change in concentration on the equilibrium position? Our problems including several of them. So to improve the air quality and obtain a useful product, chemists often remove sulfur from coal and natural gas, by treating the fuel contaminate hydrogen sulfide with oxygen. Hydrogen sulfide gas reacted with oxygen produces sulfur solid and water steam. So you balance your reaction. What's going to happen if you add oxygen? What's going to happen to water? Second one, if you adding oxygen, what's going to happen with hydrogen sulfide? If you remove hydrogen sulfide, what's going to happen with this oxygen? And if this sulfur is added, solid is added, what's going to happen with your gas? So here I want to mention one thing. Whenever you have solid is not going to affect on the equilibrium shift, or at least the effect will be negligible. What you are going to do, first of all, you are going to write down something called the chemical quotient, Q. Q equals to the product of water to the power 2 divided by concentration of hydrogen sulfide to power 2 times oxygen concentration. Again, your solid is not going to be included in your chemical quotient or equilibrium. So when you are adding this oxygen, what's going to happen? Your Q, chemical quotient, will decrease. So what's going to happen? You want to bring it back. So in that case, when you increase this oxygen, so what's going to happen? This water molecule will be increased. So concentration of water H2O will increase. So other side, the other one, let's see. If your oxygen is added, you added this oxygen, so again, this reaction will subject to the equilibrium shift to the other direction. Oxygen added, so you want to move to the forward. The concentration of hydrogen sulfide will decrease. Similarly, if you decrease this hydrogen sulfide, so your reaction wants to bring it back. So therefore, your reaction moves to the reverse. If you're adding sulfur, again, sulfur is not going to affect on the concentration change. So sorry, I think the BCD for some reason didn't show me this BCD. I will leave it for everybody to study by yourself as a take-home message. If you have temperature, your reaction involved in gas, what's the impact of pressure or volume on the equilibrium system? So this is our equilibrium system. What's going to happen? You are going to lower your pressure. When you are lowering your pressure, what's going to happen? You are going to have a higher volume. As pressure decrease, you have a higher volume. What's going to happen? More molecules will be produced. More molecules will be produced to increase this pressure. Meaning what? Meaning your reaction, if you have more gas in the reactant, so then the product, so reaction will move to the reverse. Otherwise, if you have more gases in the reactant, reaction will move to the forward. Similarly, if you have actually it's oppositely, if you have the high pressure, you increase the pressure, volume decreases, what's going to happen? Your pressure want to be decreased. So in that case, you produce less gas molecule. Again, if you have the gas molecules has a larger moles compared than the smaller moles for product, so what's going to happen? Your reaction move to the right. Otherwise, if you have fewer of reactants, more product gas, reaction will go to the reverse direction. This depends Anyway, whenever you're adding external stress, your reaction wants to move back. So we also have some questions. So three more questions. I want to see how you are going to increase the product yield if you are going to change the volume of each reaction. So the first one, if you change the reaction, if you change the volume of the reaction for the first one, what's going to happen? What's your plan? The plan is when gas are present, when gas molecules are present, a change in volume will affect on the concentration of the gas. So solid is not going to be involved in. First reaction, only carbon dioxide will be involved in. Second reaction, sulfur plus fluorine produce sulfur hexafluoride. These two gases will be involved. And then the last equation, you have 1 mole of chlorine, 1 mole iodine produce 2 moles of product. Reactant and product has equal moles. In this case, your equilibrium is not going to change when you change the volume. You change volume, your pressure similarly will also change. So let's see this. For this one, I want to increase the product yield, meaning you want the reaction for A. You want the reaction to the forward direction. So you want a reaction to the forward. What does this mean? You want to go to this way. You want this carbon dioxide to be produced more. If you produce more carbon dioxide, you are going to cause more pressure, right? So therefore, you want to decrease the pressure. You want to increase the volume in order to produce more products. The second one, let's see. The second one, you have 3 moles of reactant, 1 mole of product. So you have more reactants than products. How do you make it to the forward? You want the equilibrium shifted to the forward. Therefore, you want to increase the pressure. You increase the pressure or you decrease the volume, so your reaction goes to the fewer gas molecules. So you want to do the moving. You want your reaction move to the right. So therefore, you are going to increase pressure or decrease volume. The very last one, because the reactants and products has equal moles. Therefore, the volume or pressure change will affect on both sides equally. Therefore, no net change in terms of the product yield. No matter you change the volume or pressure. For the last one, this C, there's no product yield change. Temperature increase. Temperature increase related to the endothermic and exothermic. Endothermic meaning, so you are going to consider your heat, endothermic, consider your heat as a reactant. So you have a positive delta H. Your exothermic, consider the heat as a product. In that case, you have negative delta H. So when the temperature rises, so your K will also rise. Therefore, you may have more positive delta H for your reaction. At the temperature rises, will decrease K if your system with a more negative delta H. So that's two different impact. So again, you need to know whether your reaction is exothermic or endothermic. If it's exo, you consider this delta H is your product. If you keep increased temperature, so your increasing temperature will go to the other direction. Otherwise, if your temperature decrease, your temperature also your temperature increase, so will causing the K decrease for the system if you have the delta H, which is a negative value. So I think I have another question for everybody. So what will decrease in temperature do to Kc? So right now I gave you two possibilities about temperature increase. So if your delta H is negative, what's going to happen? Delta H is positive, what's going to happen? Right now I have take home message for everybody. If you decrease temperature, what's going to happen with your Kc? So also followed by we are going to predict the effect change in terms of the temperature on equilibrium. So this first equilibrium, what you can see, your delta H is negative, meaning this is exothermic. If it's exothermic, your reaction is considered exothermic, heat is your product. You are going to rewrite your equation. So your heat as your product, if you are going to increase the temperature, what's going to happen? So you want that temperature increase to be decreased. You want your temperature to be decreased for this one. So you rewrite your equation. This is first A, the reaction, you write in your heat as your product. If you increase this temperature, your equilibrium want to bring back. So therefore you go to the left, shift to the left. The second question, you have a endothermic. You have to apply more energy, so more heat. So therefore your heat is considered the reactant. If you increase this reactant, reaction will go to the forward direction. Yes, similarly the last one, your heat is also your reactant because this is endothermic. Endothermic delta H has a positive sign. So therefore you increase the reactant heat, so your reaction will go to the forward or shifted to the right. Yes, that's right. And then the buffer solution also affect onto the pH shifted, but buffer solution can tolerate more external stress. Buffer solution must be able to consume both acid and base without undergoing large pH change. Therefore, a buffer solution must contain an acid and its conjugate base. The acid react with external base. The conjugate base will react with external acid. The buffer solution usually consists of a weak acid and its conjugate base, or a weak base and its conjugate acid. So how the buffer solution works? I believe before we also discussed how this buffer works. Just imagine you have acetic acid and sodium acetate. So you have your buffer solution. You want to put buffer solution with equal moles of acid and its conjugate base. If you are adding this proton, what's going to happen? You're adding proton and this conjugate base. They are going to react. They are going to react, meaning you are going to consume more of this acetate. So produce water and acetic acid. If you're adding base, this base will react with acetic acid, CH3COOH. So you are going to consume more acetic acid, produce more acetate. However, even though you're adding this acid base, due to the consumption of acid and base, your pH value will not subject to significant change. That is your buffer solution. Another important observation is about the common ion effect. Common ion effect refers to the effect of adding an common all ions. So an ion, all ions, which are common to those already present in your system at the equilibrium state. This effect you call the common ion effect. Such as I have this potassium or lead chromate, which is not very soluble compound, it's slightly soluble ionic compound. It's going to break down to your lead Pb2+ and chromate 2 negative plus. So this solution, you add some chromate, you're adding chromate into it. What's going to happen? You increase product, your equilibrium shifted to the left. That is about the common ion effect. Essentially up to this point, that's all for today. Thank you so much for listening. You have a beautiful day. Goodbye.